What I'm going to do is I'm going to talk to you about the structures subsystem. That's actually the origin of kind of what I did at the labs originally. And then over time, I ended up doing a bunch of other stuff, but this is kind of my baseline, my home for me in terms of small satellites. Basically, this is going to be how the groups fall out and kind of the roles that you have in the group. So I'm going to talk about this in terms of the scope of responsibility, but basically this is your job jar. So if you happen to be the structures lead, the structures team on your CubeSat, then basically these are the kinds of things that are going to fall into your job jar and the kinds of things you're going to have to do. For most of you, for most missions, high 90% of missions, the structures team should not be prominent. There may be missions where you're trying to do some sort of 3D printing and the structure is the mission. That's not true for any of you because I've seen your missions. Don't try to get fancy. Do your job. If no one knows that you ever existed, you've done your job well. If you try to get fancy and say, oh, I can save a half a pound here and build this out of some advanced carbon fiber composite, all you're going to do is create problems. Your job is just to be there, support everybody else in the mission to pull this off and keep going. You're basically also from a just practical perspective, and I think all of you are already there, 90-some% chance you're going to be in a CubeSat form factor and likely probably 3U as opposed to anything else. Again, there might be some outliers in that, but basically that's where you're going to land. It's your most common launch opportunity. And so basically, if you're going to divert from something that's up there, then you need to have a good reason and talk to like us or whoever's sponsoring your launch and make sure that, again, you're not trying to be fancy about this and do something that really doesn't make sense. So there's two types of CubeSats. There's the rail mounted and the tab mounted stuff. So they're shown here, and there's actually a better picture on the next slide. But basically, there were a couple different standards as the CubeSats were developed, and they fell out into these two. For the rail mounted, there's actually a couple of options there. And so it gets even more complicated than that. And again, a couple of future slides will kind of go through them. But this is kind of basically where you're falling out. If you know what your launch is, which you probably won't, then you can say, okay, I know I'm on this launch. You can ask them, what am I going in? They'll tell you what you're going in. And then you can say, okay, I'm designing to that standard. Lacking all of that, then you look at UNP2. And that requirement is telling you basically this standard, the Cal Poly standard, is the most generic. You will fit in the most places. You won't fit if you do that into a tab mounted system. But we're playing the game of we don't know the launch. And so we're trying to do the best we can to make you the most compatible with everybody. What we're trying to do here is just give everybody a reference so you can say, okay, where do I go look? Where do I find out the standards for this sort of stuff? Where do I get the basic information? This is the most recent that we have. It does evolve a bit over time. But honestly, in the last couple of years, it has actually settled a little bit. And so it should be pretty standard. But this is the best place to start. For these systems, you will tip off when your satellite comes off. This won't be your problem as the structures group lead, but this will be a problem for the satellite. So there's going to be a number of constraints that go in CubeSat land, things that you got to do and you got to deal with. And one of them is you basically have to come off without being fully alive.
Then user closes the door. So click is heard. The electrical interface to the launch vehicle is a DB9 socket connector. Now to initiate okay. The absence of gravity, the payload will continue to pull it all the way up.
Yeah, so that gives you a pretty good visual of how all these systems basically work. It's that little thing where you stuff the scary clown head into the box, you crank it, the lid opens, and you come shooting out. That's how all these systems basically work. But again, for the structures team, you're going to have to deal with how that interface works. And I'm going to talk about that in a little bit. But as a team, you're going to have to deal with, hey, I'm not really fully alive when I come out, and I'm going to tip off, or I have to plan that I'm going to tip off. You might not, but that's at a mission level things that you're going to have to deal with. Again, in terms of your job jar, what are the things that you're going to have to deal with as the structures? You're basically going to have the volume. I'll show you this a little more on a couple of the other slides, but because of the nature of how things have advanced, you can have unbelievable CAD capabilities at all of your universities. And so what's going to end up happening is you are going to become, as the structures group, the lead of where does everything go, as well as all of the promotional cool pictures of your satellite that will become part of your job. Just accept it. But what you're really trying to do there from a technical perspective is say, where does everything go? And you're going to become the master of that. You're going to have to deal with the deployer. There's a lot of nuance in how that all works and some struggles that you're going to have mostly at the very, very edge. So when you get to your CubeSat, you say, oh, here's the form factor, you throw it in there, that's easy, right? You're right. But anytime you start dealing with deployables on the edge, solar panels, now you're getting really close, and you're going to have to really start watching tolerances, the switches and how they interface. So you will have a job jar that goes with that as well. And then there's the basics of it in terms of safety. So again, you do not want to be someone that people pay attention to. You do not want to have a very fancy mechanism or a very fancy deployable or a very fancy structure that makes all of those safety people want to look hard at you. You want to have a simple system that they've seen a million times before, and they look at your documentation and they say, we're done here. That's what you want as a structures group. So again, in that simple, what we recommend very, very, very strongly is that you use 6061 T6 aluminum. Again, that's something they've seen 1,000 times before. They understand it. If you go back in the archives of SmallSat, of the papers of what everybody did, they did that. You basically need to have a very, very, very good reason why you're not doing that. And we'll probably still tell you no. If you're flying through us, that's what you're going to do. The other kind of pieces that go into this are outgassing. This typically falls into the structures group job jar, maybe not, but you need to make sure that you don't have nasty things that outgas when they get into the vacuum of space. These are typically plastics, adhesives, those sorts of things. The website is on there. You basically just go check and say, okay, everything's good to go. They have these two things they call TML and CVCM, and they're basically just different ways that stuff outgasses in a vacuum. There's limits. You work through that process. The other thing that often falls into your job jar, maybe somebody else's, is demisability. And what I mean by that is, as a satellite, you need to show before you get launched that your stuff is not going to re-enter the Earth's atmosphere and land on somebody's head or a cow's head or whatever and kill them. So there's a thing that gets done there. There's paperwork. It's not that hard for a CubeSat, unless you're doing something completely weird, like flying a huge block of something very, very dense, or having a tank that is very, very light. That's actually, ironically, the other way that things come back in, which none of you have, based on what I've seen. You just do the paperwork and you'll be good to go. So this goes back to what I was telling you about the CAD. You want to start simple, and you probably want to follow this up with physical things as well. So often we see a group that will come and they'll just 3D print if they've got it. They'll build it out of cardboard if that's all they've got available to them. Although at this point, I think you probably all have 3D printing available. So they'll do just a rough model of boxes, just to see as you watch this progression as things go together. And then eventually you will end up with the picture on the right. And as I said, you'll use that technically to figure out not just where everything goes, but also, can I get a tool in there? Can I get a wiring harness in there? Can I get a hand in there to adjust whatever I have to adjust or insert whatever I have to insert? And then oftentimes what will happen with that, and I think this is actually on a future slide as well, what is the assembly procedure? So I can't get at said bolt unless this other piece is off. And so I say, okay, then I have to assemble the structure this way. But then if I disassemble it, am I hosed? Can I even do that? So we'll talk about that when we get to the next one. The other piece that's going to happen is you're going to have to make your structure. So you're going to probably have, you know, the 6 panels and some other maybe interim panels, that kind of cross panel kind of stuff. If you go back in time, the way that that process worked is you did a drawing of the part, you sent that drawing to a machine shop, that machine shop made the part and sent it back to you. That's all changed pretty much depending on how your university or how your system works, where you just do the CAD model and you send them the electronic CAD model. And so that process has gone from a paper-oriented process to a digital process. Again, it's not pure at this point. However that works in whatever process you're going to use. So oftentimes you'll use the machine shop at your university. You may end up sending that out. There are folks right now that will just take a CAD file and just send you the part back with not much other interface. The important part though is don't lose track of there's going to be a learning process for you as you go through this. It's not going to be as simple as I design the part, I send them the part, and I'm done. You are going to run into things that you do not know that you do not know, like tolerances, like how thin can I machine something before it warps on me? What are finishes? What is allodyne? What is anodize? All of these sorts of things, too much to go into now, but it's important that you establish a relationship with someone in this world. And the easiest person is the person who runs the machine shop at your university. And you're going to work through this process and you're going to learn these things. And it's going to be easier if you have somebody who's helping you, teaching you, rather than you bumbling around and trying to figure it out yourself. The other piece that will fall often into your job jar is mechanisms. Most common is you may decide that you don't have enough power, and so you need a deployable array for your solar panels. That's very common. As I told you, when you get back to the deployer and fitting that at the edge, that's going to be hard, challenging, but something you got to definitely pay attention to and work through. The other kind of things that tend to come up are antennas, maybe, or some sort of deployable. Often if you're doing any sort of instrument that's sensitive, often space, weather kinds of stuff, you want to get your instrument away from the satellite. And so those are kind of the 3 most common categories we've seen. Again, in structures land, if you don't have to do it, do not do it. So you're going to present over the next couple of days and you're going to say, I need X amount of power and that requires deployable solar arrays. And somebody in this group is going to say, prove it to me. Because if you do body mounted, your whole life just gets easier. And so if you have to do deployables, fine. But you need to know that you're taking on this complexity for a good reason. And that's just true across all of doing a satellite. Now we're kind of getting into the further out stuff. Your main job is to do the structure, but eventually you're going to have to worry about how do I package that? How do I put it in a shipping container? How do I take it on an airplane to get to the launch site? How do I do all that? How do I pick it up if I need to pick it up? How do I turn it over? Do everything that I need to do at the satellite. So you do not want at this point to have this be some sort of exquisite design. You always want this to follow your design. Your design for your CubeSat is maturing and this is always trailing. But what you don't want to do is do nothing. You want to just kind of be thinking of this in the background and saying, what are the unique things I got to do? How have people done this in the past? Because again, eventually this is going to fall into your job jar. You will be responsible for the mass budget for your satellite. Most likely somebody's going to be, and it's a very simple spreadsheet. You basically just say, here's all my parts on my satellite. Here's my estimate of how much they weigh. And at the end in Excel in the corner, here's my total. You do want to carry contingency on that based on what you know, and that number should go down. So the recommendation is 25% in the beginning, even if you think you know what you have, because you've picked whatever satellite supplier. They may go out of business by the time you go to buy them. They may be on a next rev by the time you go to buy them. And so you're like, I know what I have. Well, there's always uncertainty in this process. So keep that fairly high and then let that run down as you get to the end. The honest answer in CubeSat land is I have personally never seen somebody get overweight and have the deployer / launch vehicle people have a problem with it. That just doesn't happen. You're not going to get overweight on a CubeSat. But what we, if you go through our process, want you to do is go through the rigor to understand the process. So we're going to make you do this anyways. There's internal reasons why you probably want to do this as well. If you're trying to do any sort of ADCS on your system, you can't do that unless you know how much you weigh and how that's distributed. So you're going to have to do this internally as well. For the volume, it's really just an issue that if you go back to that CAD model, just making sure that everything fits. We've seen people in the past come up with some sort of thing that says, like, here's my Excel spreadsheet, here's everything, and here's the cubic centimeters. That doesn't tell you anything. It doesn't tell you anything. So you could have a volume that theoretically fits, but it's something that's this long and this big around, and it doesn't fit in the factor. So make sure that the tools are doing what you need them to do. Don't just do the tool blindly, is the point for that. This is really, from an analysis perspective, the biggest piece of what you will do for the structures group. You will make your structure to hold everything. And then from a safety perspective, you will prove to that community that when they open that door, pieces of everything won't come flying out. That's your job. And this is how you do it. So there's two kinds of loading that we characterize for a launch vehicle. So if you just think about a launch vehicle, it does two things. It goes up like crazy and it shakes like crazy. And the top one is trying to capture that quasi-static load of, hey, it's accelerating like crazy. And then there's some weird things that happen like wind gusts and turning over, but basically it's trying to capture that quasi-static part. And then the shaking part is the bottom part. For the analysis, you're really going to go into a finite element program and you're going to do the top part. The analysis programs right now, depending on what you pick, will tell you that it can do the bottom one, but that really comes down to best practices. It will give you an answer, but you got to be really careful about overusing the tool. It really isn't meant for that. You're really in the top one looking at, does my structure hold together when I just accelerate like crazy in the rocket? And then the bottom one, you're saying, do I have like things hanging off boards or weird wobbly things that when I just shake this thing really hard, they're just going to crack and fall off? The structure itself is going to fail in the top one. The piece parts inside in general are going to fail on the bottom one. If you take a solid piece of aluminum and shake it as hard as you possibly can, it doesn't fundamentally care. It's the top one that could cause it problems. So this is just a little bit more on that. To be clear in the process, we have given you one number, which is the 30 Gs. The way that we got to that is we basically took all the envelopes for all the launch vehicles that are out there, picked the worst ones, applied the worst factors of safety, added even a little bit more and got you to 30. So don't add anything to that. Don't add a factor of safety of 2 to that. Don't assume you need a margin of safety. There's all this stuff that happens in that world with factors of safety and margins of safety. We tried to go there for a while and it got just too confusing for everybody. So it's just designed to 30. If you get there, if the thing doesn't fail at 30, you're done. Keep going. For completeness, you'll go to our test facility and you'll basically see every one of these test capabilities, basically, in the lab. Not all of them, actually, but these are all the things that could happen on a satellite. From a practical perspective, the things that you are likely going to see are row 2 That's the random vibration. That's the bottom one that I showed you, where we're going to stick it on a table and we're just going to shake it really hard and see what happens. That is not the quasi-static piece that I talked about. That would be the top one. And again, typically we don't even bother with that test. We show it by analysis. You use aluminum 6061 that they've seen a million times before. We show high margins and no one even asked for the test. As much as anything, that random vibration is a workmanship thing. So you didn't do a good job soldering. You've got bolts that are loose, little tiny bolts that are holding things on, typically not the big ones. It will shake out any, literally shake out any of that sort of stuff and say, nope, we got to fix this. If you have a very large structure, that will get into more of the acoustics of it, but none of you do, and so that won't happen. So you'll do random vibe. You could do a modal survey to figure out your first modes of your structure. You won't. Again, unless there's some really weirdness going on, you probably won't. You can also characterize, put it on a table, a rocker table, and figure out exactly where your CG is. You probably won't, but we could if you decide you need it at the end. Some people do pyroshock testing if they've got something that's sensitive. You probably won't. What you will do is some combination of the random vibe, most likely, and some combination of those bottom three. Those three are basically in order in terms of how hard they are, but also how much you learn. So the bake out you will do, most likely. And what that does is you basically just heat it up. And if you screwed up, you're outgassing a whole bunch of stuff that you didn't catch will outgas. And it won't hurt anything because it's literally just like your oven in your house. The next one is what you're trying to do is cycle that back and forth. So you're going hot, cold. So it's not just an oven, it's a cooler, and they have devices that will do that for you. When I'm in the sun, I'm going to go up to this temperature. And when I'm on the cold side, when I'm in the shade at night, then I'm going to go down to this. And then the ideal test, which is the most expensive test, is the thermal vac. You're going to land somewhere in all of that. So you will do some thermal testing. It most likely will be associated with a little bit of safety and a lot of you figuring out that you can survive this, but that's the most likely test scenario. That's it. Questions? Yes. So the question is for the Zoom folks, when you have commercial off-the-shelf COT stuff in structures land, what's the advice? So the generic advice beyond structures is all spec sheets are lies. All promotional materials are bald lies. None of them are true. So every single thing you buy, I don't care what it is wrong. It's optimistic. So somebody somewhere in the past said, trust but verify. You have to verify every single thing for every single thing that shows up on a spec sheet. For the main part of the structure, that's the one part that you may not actually buy. It's getting to the point where a lot of the ADCS battery, a lot of the subcomponents have matured to a point where you as a university can just go buy a lot of them. The structure you can also go buy, but it is very much attainable by you as a university, and it's a cost issue. And so we see a lot of the universities actually making their own structures. You can do it. It's not hard. You just need a machine shop and some time. And so a lot of folks actually on the main structure do it themselves. And from an education perspective, awesome. From a mechanism perspective, because that's the other thing that's likely to fall into your job jar. Again, spec sheets are all lies. In terms of COTS world, I think the other big piece of advice, the big trap that we see all of the teams fall into is you think that when you go buy something that you're done. And all you've done is bought off a different pile of work. It's a less pile of work, but it's a different pile of work. So you're doing things like verifying how the spec sheet is wrong. But then also, if you built it, then somebody's going to come to you and say, prove to me you built it well, as one example. And if you bought it, they're going to say, prove to me that the person that you bought it from, like, what traceability do you have on that part? What certification are they providing? And did you track that the whole time? Because that's what gets you to the end state of, hey, I'm okay with this thing. I'm not worried about it coming out in pieces on the launch vehicle. Yeah, so the question is, basically in the charts, we show the main loading that the structure is going to see, which is the quasi-static and the vibrational loading. But there are other loads. There are pressure loadings that can come about because you're going into a vacuum. There are thermal loadings because you're going to get really hot and really cold. You may end up with some sort of inertial loading, as you said, if you're spinning. You do have to pay attention to kind of all those other ones if they become important for your system. The inertial loading, the tip-off loading, in general, if you buy anything, you really probably won't have an issue. You have to look at it, but generically, you're probably going to be fine. For your mission, if you're not locked dead set, there's no way in heck you should be pushing a button to say go. And when these things are locked down, they have to survive 30 Gs. They can survive a little bit of spinning. Again, you have to check all this, but in general, it's fine because it's locked down to survive 30 Gs. It'll be fine with the little bit of spinning. The thermal, especially with any sort of deployable, you have to be very careful because it's not the fact that the whole thing gets hot. It's the fact that part of it gets hotter than the rest of it because part of it's further out towards the edge of your satellite. And that's what's really going to cause you problems. So again, if you're purchasing something, this is a common problem and these people have thought about it. And so you can talk that through with them. They have hopefully thought this through. And if not, then you probably don't want to buy from them because this is a very common problem. Same with vacuum, which is probably pretty far down the list in terms of actually being a problem. Yeah, so the question is for the MGSE. The fact of the matter is that for a 3U or even a 6U, because it just doesn't weigh that much, as long as you're careful about how you design it, you basically can just use your hands. If you have, for example, body-mounted solar cells everywhere on the satellite, you can't just use your hands to pick it up. So you got to be smart about how you do it. In 12U land, you're kind of on the line about whether you need help to pick that up or not. And some places have rules that will basically say you have to pick up a 12U. We don't care. We're not going to let you do it because we're Boeing and this is our safety. So there's a lot of it depends in all of this. And I think there's only one of you that has a 12U that would affect you. It really comes down to the mass, right? So let me kind of just go back to the generic of you have a 3U, right? What do you need to do with that 3U? From an MGSE perspective, you need to be able to put it on the table and work on it. And you're not just going to take the satellite and throw it on the table with solar cells and antennas. So you need some sort of cradle that's capable of getting at all the different sides that holds it on the table so you can work on it. And that's 3U, 6U, 12U. You need that. You're going to need that, period. The other thing is you're going to have to ship this. Now, you may decide what a lot of people are doing is for a 12U, they will buy a plane seat and they will stick it on the seat next to them. Or a 3U, they'll just put it in a little Pelican case and bring it as a carry-on. But nonetheless, you've got to be able to put that in something and bring it somewhere. That's going to happen. The rest of it is, it depends. And so if you don't know for sure, you're going to have to kind of consider how you would lift this thing above the CG and move it around. I mean, my honest answer at this point is I would get further along in your design before you get crazy about worrying about that, because you need to kind of have a sense of what vehicle am I going on? Am I going through UNP or am I going through NASA? And then like, if you're going through UNP, then you can ask the program office, look, here's what I have. What do you guys think? Because there's ways that we can kind of work through that process where part of that happens at our facility that you'll see and we control, and we can be, you know, Boeing has this rule that's NASA safety driven or Air Force Space Command driven, and no one gets to change those. And so you can kind of two-step that down the path. But again, it is a mistake for you to overthink that too early. You want to kind of let that follow the process, not have this detailed design of exactly how you're going to lift it tomorrow. You're getting ahead of yourself.
All right. Hello, everyone. Hopefully you can all hear me. I used to do a lot of outdoor activities, so I can hopefully still project my voice. So getting into kind of an introduction, why should you listen to me is because I wrote that. The other reason why you should listen to me is that thermal is complicated, but not hard. And everything that I learned was just by trial and error. So for those of you who are actually working on the thermal system, I know exactly where you are right now, which is you have no idea what's going on and you think this is the hardest thing ever. It's not, it's just complicated. So this presentation has been developed based off of the thermal guide, which I wrote and which was reviewed by Dr. Derek Hengeveld and also reviewed by Emmy. So there's been a lot of work that's gone into this. It's not technically a book yet. Maybe it will be soon if I have my way. Okay, so the purpose for today is we're not going to teach you everything there is to know about thermal modeling. That's just not going to happen. However, what we are going to do is introduce the methods and concepts used to develop a small sat thermal model, and that can be applied to every single one of your missions. Thermal modeling can be applied to all of them. It's not that specific, at least we're not going to get that specific today. Also, we're going to understand why thermal modeling and thermal analysis is important, or they are important. I'll get to that in just a second. Some common pitfalls, and then we'll talk about some resources. There are a lot of thermal modeling resources out there. Half of them are wrong because half of the people that write those papers don't know what they're talking about whenever it comes to spacecraft thermal modeling. There's a very, very big difference. If you're a ground application and you read a paper and they talk about how to do something in SolidWorks or ANSYS, that's fine for them. If they're talking about how to do it in space and they're doing the same methods and approach that would be otherwise done for a ground-based system, they're probably wrong. So you need to take that with a little bit of grain of salt. Thermal is thermal, whether you're in the space or on ground, but the applications and the pitfalls can be very different. So use those resources at your own risk. But hopefully our thermal guide is helpful. Also, thermal control handbook, various other ones are out there. So if you don't have resources, talk to Emmy, talk to myself. We can make sure you have those resources. Also, I am a UMP alum. I was a thermal subsystem lead for the Missouri S&T small sat program. So I do have some experience. Yes. So what is thermal? Thermal, outside of a catastrophic failure in your power subsystem or your structures, is the fastest way to turn your $100,000 satellite into a flying brick. It is the program that if everything goes right, they will never care about you. And if it goes wrong and they know it's thermal, then they're going to be like, why the hell did you mess up my spacecraft? Because it got too hot. It shouldn't be hard. It's just thermal. So that's the pitfall. Thermal engineering is hard in that respect. So what is a thermal subsystem responsible for? It is responsible for ensuring the spacecraft does not get too hot and does not get too cold, and that components within inside of the spacecraft that have specific thermal constraints do not get too hot or too cold. You are playing a bounding game. You want to make sure that things don't get too cold whenever they are in eclipse, and you want to make sure things don't get too hot, and that is your job. So there's a couple of different steps in there, and we'll get to most of them in this talk. Okay, so yeah, so within allowable thermal limits, how is this done? Through thermal modeling and testing. So there are two things there, thermal modeling and thermal testing. Testing, we've already introduced a little bit where we've talked about thermal vacuum test, the bakeout, thermal cycling, and I'll talk a little bit about those. Those testing are used for a couple of different purposes. The bakeout, as we already mentioned, is used to bake out all of the components to make sure that it's not going to outgas in space. That's all well and good. There is thermal balances and thermal cycling. So those are used not only to test the spacecraft physically to make sure that it doesn't break, but also to give you information about your thermal model and see if you can compare your thermal model and say, wow, my thermal model says I should be 50 degrees Celsius, but my testing says I'm 30. Well, that could be a problem. So testing isn't there just to give you a thumbs up. It's there to give you information about how good a job you did, because until you test and compare, your thermal model might be as good as a 5-minute hand calc, and you may never know the difference. So unless you test it, you're not going to know. So a good thermal design, though, once you set your constraints and you know what your thermal bounds are going to be, whether it's going to be, well, I can't go below -20 or I can't go above +50 Celsius. Once you know what those constraints are, then you need to design a good thermal design for your spacecraft that's going to meet those requirements. You're not the James Webb Telescope. You're not trying to do something insane. You're trying to meet these spacecraft thermal requirements. Don't make your life harder than it needs to be. So if you have a very, very strict thermal design requirement that you really can't break, then your life will be more complicated. If it doesn't need to be that complicated, don't give yourself more headache, because then you're just going to wind up making a mistake, because that's just how that works. The more complicated things are, the more mistakes you might make. You must also balance thermal design with power requirements. You don't have unlimited power. So why could this be a problem? If you have a spacecraft that's in your thermal model, it's telling you that you're getting cold a lot of the time. You're getting into that lower threshold and you're like, wow, okay, well, this is a problem, but I can fix this. I can just put some heaters onto my spacecraft and then it's no problem. What's the problem with that? Heaters consume power. So if you have a limited battery supply or no solar panels or whatever the case may be, then you're going to have to ensure that your thermal design doesn't negatively infect the power requirements or the structure requirements, as it may be. You have to play within the constraints that you are given. So you don't have unlimited power, you don't have unlimited space, you have limited resources. So if you design your spacecraft in such a way that you're having to use 10 watts of heater power to keep your spacecraft from freezing to death, you need to redo your thermal design, probably. Okay, so thermal design is an iterative and multidisciplinary process. Why is this the case? Because everything has a temperature and everything is touching each other in space. You cannot make a thermal design of your spacecraft without talking to power, without talking to structures, without talking to the electrical system. Everything on a spacecraft either is going to be a source of heat loss into space or a source of heat gain from electrical heat. As electrical components use electricity, they're going to dissipate heat, and you have to worry about that as a thermal engineer. So you have to talk to every single other system on a spacecraft to understand what their requirements are, i.e., what temperature they can't exceed or can't go below, and then how their design is going to impact not only your thermal design, but then everyone else's thermal design. So really, the thermal subsystem is just about the best systems engineer on the entire spacecraft outside of the systems engineer or program manager, because they have to touch every single other subsystem. So in other words, don't take off your other subsystem leads if you're working with thermal. Be nice to them, you need them. So iterative process, you have thermal modeling, which is the process of capturing the thermal characteristics. You're trying to model reality, create a model that corresponds to reality. Then you have analysis. Analysis is separate because you are simulating that thermal model in a variety of different ways, in hot cases and cold cases. Those two things are slightly different. For different analyses, you might have to tweak your thermal model to make it a little bit different. So a good thermal model plus a good thermal analysis equals a good thermal design. Another thing you could add into that little equation there, a pseudo equation, is a good thermal model plus a good thermal analysis plus good thermal hardware in actual application of everything equals a good thermal design. Okay, so what goes into thermal modeling, analysis, and thermal controls? A lot, basically. If you can't read it, you have to worry about the orbits. Orbits will affect your thermal performance greatly. Material properties, optical properties, the mission parameters, mission modes. If you have a very, very complicated mission with multiple mission modes, with multiple electrical requirements, you're going to have a more complicated thermal model. Same thing with the attitude of your spacecraft. Are you primarily nadir pointing or zenith pointing? Where are you looking at? That's going to also affect. Payload requirements, mission lifetime. If you're flying essentially a 3U CubeSat with a couple of batteries that's just going to exist for a couple of weeks, then, well, you're not going to have that complicated of a thermal model because you just need to make sure it lasts for 3 weeks. That will be different if you have a year-long mission somehow. Then you're going to have a more complicated model because you have to predict what's going to happen over the course of a year in a variety of different operating conditions. So all of those things and more are your inputs. So this is a game of inputs and outputs. On the one hand, you're a customer. You're asking for things. Please tell me information about my satellite. And then you are going through this iterative process of, I'm going to model it, then I'm going to analyze it, then I'm going to apply thermal control, which is the application of heaters or changing some design. and then I'm going to do it again and again until it works. It's not a linear process where you do it once and then you just kind of kick it out the door and say, well, I hope that works. You will have to keep doing it for a very, very long time. Good thermal models start early. If you are a team that has a young spacecraft, start your thermal model early. Don't wait until you have a design 90% nailed down and then suddenly you build a thermal model that says, oh, that component's getting like way too cold there and we can't do anything about it now because we've already bought our subsystem hardware and everything else. That's a bad way. So don't do that. So you're going to go through that process and then you're going to start generating outputs. A systems engineer or those other subsystem engineers and leads, they don't care about every single analysis result that you will create whenever you do a thermal model. What do they actually care about? Well, they care about temperature. All they want to know is, am I going to exceed my temperature limits or on the max or min? Am I not? Am I, like, tell me. That's what they care about. Same thing with temperature gradients. Some things like optics or other sensitive components are going to have gradient requirements. So you don't want to have one end of a component get too hot and then another get too cold. That could cause some structural stresses or mess up the sensor or whatnot. So they might care about that. Heater power. So your power subsystem is going to want to know, hey, are you going to use up all my power budget whenever you're in eclipse or not? They're going to want to know about that. And then any kind of thermal control requirements. So thermal control. What is thermal control? Thermal control is the act of taking the information that you get from modeling and analysis and saying, I need heaters and I need different optical requirements. And we'll get into what optical requirements actually are. But those are your outputs. So you're feeding a little bit of design information back out and a whole lot of temperature information. But if you are a thermal modeler who's going to be doing this, you're going to have to work in this, taking inputs as a customer, and then I'm delivering things to other people. And so you're going to have to switch up your language and get really, really into the details on some ends. And then whenever you're presenting the information, boil down to what's important. What are the temperatures? Am I within my operating conditions or am I not? Sidestep. So thermal, as I said, kind of touches a lot of different things. So this presentation is going to kind of bounce around to a couple of different topics because all of them are important. So orbits. Orbits are complicated. For thermal, they're not. There's only a few things that you care about as a thermal modeler with respect to orbits. One of the primary things is going to be your altitude. If you are very, very, very far away from the Earth, you're going to be colder. For the purposes of this talk and for just thermal engineering, imagine the Earth as essentially a giant space heater. It has heat, the Earth has a temperature, and it radiates heat away just like under a thermal camera, we radiate heat. You ever seen a thermal imager of someone, and you see a hot thing represented as, a warmer color, and then a colder object represented as a cooler color? That is a thermal image of infrared radiation that is being emitted off of a body. In this case, the Earth does the same thing. So it's going to have radiation that is coming off of the Earth and is going to passively heat the spacecraft. The closer you are, the more heat you're going to be absorbing. The further away you are, the less heat. So you're going to care about your altitude. You're also going to care about your eccentricity. If you're going to be going super, super close on one end and then all the way over here, you're going to be very, very, very far away. That could cause some issues. Why? Because for 45 minutes, you're going to be very, very close to the Earth and getting a lot more heat. And then you're going to be very far away, losing a lot more heat. So that cold to hot could cause issues. You will also care about your inclination. So basically what that means is, am I orbiting just around the equator? Just, kind of normal, like most pictures of orbits do. You're just going around the equator. Or am I going to have an inclined orbit? So am I going to be going across the equator, then to over some colder areas, and then back across? And then, it's the same kind of thing. Hot, cold, hot, cold. That's going to mess also with how you absorb sun. So you care about orbits as a thermal engineer from the perspective of how does it affect my heat absorption and my radiation. You don't need to become an orbits expert. You just need to understand enough to do your work. And that's kind of the motto for most of thermal. You don't need to understand all of the power subsystem, just enough so that way you can get your job done. For some of you, like Missouri S&T, you literally have an orbits expert who's the advisor. So you're well off from the orbits department. For the rest of you, if you don't have an orbits advisor, get one. They'll make your life easier. Orbits is important, but you don't have to understand everything. The most important thing, though, is beta angle. So what is a beta angle? Well, I'm going to start by saying what it isn't. A beta angle is not a orbital parameter. So if you review orbits and you're looking through your orbits textbook or talking to an orbits person, and you're just like, why can't I find beta angle as one of the properties of an orbit? That's because it isn't. Beta angle is a description of how the vector of sunlight that is coming from the sun, how it hits the orbit plane, and how that affects the heat absorption. The beta angle is measured from the solar vector coming in reference to the orbit plane. So if you have a beta angle of 0, that means that your orbit plane is parallel with your solar vector that's coming in. And what that does is if you go around the Earth, you're going to be going in and out of eclipse, which means that you're going to be sometimes getting the sun and then sometimes not. And then sometimes you're going to be getting the sun and then sometimes not. If you incline the beta angle enough, you're going to actually be getting sunlight the entirety of your orbit. So if you have a beta angle of around 75 or 80 degrees plus, that means your orbit is so inclined that you are orbiting over the poles to where you're always in sun view. That is a very, very different thermal condition than if you are in a normal orbit going in and out of eclipse, because that means that you're always going to have the sun and you're not going to have a chance to radiate away that heat. For small sats and UNP, I certainly hope you're not in a beta angle of 80 degrees plus. I guess it's not impossible, but you're probably not going to have that problem. However, if you are doing thermal analysis, beta angle is important. So keep that in the back of your mind. Most of the time, whenever you are doing thermal models and thermal analyses, one of the things that's going to be contained along with your deliverables is going to be what beta angles did you simulate. We'll get to some of the beta angle things later because there are some pitfalls with what you do with beta angles. Another thing about beta angles, though, that is important for those of you who have long satellite missions. If you have a satellite mission that's going to last a month, this slide doesn't really apply. For those of you who have satellite missions for longer, this does apply. Beta angle varies with time. There's a whole lot of orbits information for why that is, but basically just condense it down. The TLDR version is that beta angles change because the Earth orbits around the sun, and there's a whole bunch of math and angles involved. That's the TLDR. Basically, that means that you can have varying thermal conditions throughout your mission lifetime, especially if it's a fairly long mission lifetime. So if you look at this graph, though, you're going to see number of days since the vernal equinox, so essentially a date and time, and then beta angle variation. And so this is, I believe, actually for the ISS. So it has an altitude of 408 kilometers and a circular orbit or near circular orbit with an inclination of 51 degrees. That's an actual orbital parameter, so orbital inclination. Its beta angle is going all over the place from 0 to 60 to negative 30, all the way up to 75. So it's all over the place. So if you're actually going to have to get into the nitty gritty, you will have to consider that. Beta angles, the main use for them, though, is determining what your cold case is and what your hot case is. And I believe there's a graph. So cold case and hot case. What is a cold case and a hot case? Okay, so say that you are the thermal modeler and you are told, please model my satellite and tell me all of my thermal conditions. And you're like, great. What conditions would you like me to model? And they're like, all of them. And that's a bad thing. If you just try and model all of your thermal conditions, remember that graph, you're going to have to go through every single beta angle all over the place. It's going to be a nightmare. There's a way to condense all of that down. You have a cold case and a hot case. So what's the logic here? If you have a hot case, what you're trying to do is model what is the hottest possible that the satellite could experience. So worst case scenario on the hot end. And then you have a cold case. A cold case is what is the worst conditions that I could experience on the cold side of things. If it can survive the coldest and it can survive the hottest, it can probably survive everything in between, right? You don't have to model the universe. You just have to model the worst case scenarios. That will change if you have lots of mission modes. So it will essentially kind of factorial out to where, well, if I have this many mission modes with this many different parameters, then I'm going to have X number of cases I'm going to have to simulate. So you don't have just two. It's never just a hot case and a cold case. There are multiple, but you boil it down to thinking about what's the coldest conditions possible and what is the hottest conditions possible. This is the number one dumb mistake that I see made whenever people start doing thermal analysis with regards to orbits, is they're like, cold case, that's going to be a beta angle of 90 because I'm orbiting over the poles. That's my cold case, right? I have had people do that. And the answer is no, that's not your cold case. Look at the orbit. If the orbit is above the poles and I'm in a beta angle of 90, what's my sun condition? I'm always sunlit, which means I'm going to actually be in my hot case. So don't make that mistake. A cold case is going to be a beta angle of 0. Why is that? Because a cold case, a beta angle of 0, is maximize the amount of time that you spend in eclipse. So what's that do? If you're in eclipse, you're on the shaded portion of your orbit. So the sun is on the opposite end of the Earth. You're in nighttime. What doesn't exist in nighttime? The sun, which means that you don't have a giant freaking spotlight shining on you, heating up your spacecraft. So that's why a beta angle of 0 is a cold case. You're maximizing your time spent in eclipse. You're, again, probably not going to have a beta angle of 90 degrees. That would be rather insane. That's actually a really, really hard orbit to even launch into. So I wouldn't worry about it. And so here's the question. If you're a thermal modeler and you're trying to model the maximums and minimums of your possible mission, if you're not going to be in a beta angle of 90 degrees, should you model it in 90 degrees? I hope everyone's like, no, shouldn't. Why? Because that's not in your mission. Don't model what's not in your mission. If your mission is to go to 90 degrees, then model it. If it's not, don't model it. That's not your hot case. Your hot case should be whatever your maximum beta angle is. And so a cold case is always going to be 0 degrees. That's just the standard for how to do it. And that's a pretty good approximation because many things are in a beta angle of 0, and that's fine. Every satellite goes into, crosses 0. Actually going to go back. So see here, even though the beta angle is going to be going all over the place, see the places that it always crosses? Crosses the axis, it crosses 0. So you're always going to have a case where you're going to have a beta angle of 0, no matter what you do. You're always going to have 0. What you are going to have, though, is a maximum possible. Look up your orbits textbook, talk to your orbits person. They will tell you the simple formula. It actually might be in my book. I don't remember. If it's not in my book, look up in the thermal control handbook. There's an equation that will tell you, based off of your actual orbit parameters, your Keplerian orbit, what is my maximum possible beta angle? Figure out what that is, figure out what the maximum possible beta angle is, and model that. If it's 75 degrees, model it. If it's 30 degrees, model that. All of that information, it was a lot of here are some different things that you have to consider because that's just kind of the way the thermal subsystem works. You have to consider a lot of things. Now we're going to start digging into a little bit more specifics about, okay, that's great. I'm glad you told me about the orbits, but how do I actually model it? Because that's my problem. Okay, so we're going to actually talk about that now. I'm going to assume that none of you have had heat transfer, or if you had, it's been, a semester ago and you forgot half of it by now. So you have 3 forms of heat transfer. You have conduction, which is through a physical object, like actual molecules that are together, that are conducting heat from one atom to the next, and that is conduction. Then you have convection, which is, air flow, right? And then you have radiation, radiation being energy emitted in the form of electromagnetic waves. In space, no one can hear your scream because there's no air, so cheap alien reference there. But there is conduction and radiation. So do you care about convection? No, good, because convection is hard to model, so you don't care about it. But you do care about conduction and radiation. So conduction is going to be anything that is touching on your spacecraft. Your structures, your optical parts, your sensor components, your solar panels, all of those are bolted together. So there's going to be conduction through those components. You care about that. And then the harder part to understand, but actually the easier one to model, if you're using a program, is radiation. Everything has a temperature, and therefore everything is radiating away heat. everything, absolutely everything. Because of that, you're going to have some parts of your spacecraft that are going to want to get colder because they're very, very large, like solar panels, and have a lot of surface area and are radiating away heat. And then some components that won't want to get as cold because they're inside the spacecraft and they're not radiating away heat to deep space. We'll get into more specifics about that in a second. If you do have a spacecraft that is low and very, very fast, this is not for you guys. I'm just saying in the future, if any of you do actually take this up as a career and hobby, you do technically might have what's called free molecular conduction, which is essentially you're running into molecules in the upper atmosphere that could actually give you a little bit of heating. There is software to do that. So sometimes you actually do have to worry about the upper atmosphere, but for like 99.9% of the time, you don't. I love this orbits diagram. I don't know why, like this just really captures it really simply. So I've already mentioned you're going in and out of eclipse. This is kind of what that looks like. So I'm going to start over here on the left. So you have a spacecraft. It is on the sun facing side of its orbit. So it has the sun on one side and the earth on the other. Where's the heat coming from? Well, it's getting direct solar radiation from the sun, and then it's getting what's called Earth IR, or Earth infrared radiation, coming from the Earth. That's just that infrared heating that's coming from the Earth. And then you have albedo. What the heck's albedo? So albedo, depending on the physicist you talk to, actually has a couple of different meanings. From our perspective as a thermal engineer, albedo is the amount of reflected solar radiation. And this was always in all the textbooks that I saw, but you have this diagram of you have 100% of the sunlight coming down on the Earth's surface, and you have so much absorbed by the clouds and so much absorbed by the Earth's surface, and then some of it's reflected back out. Well, albedo is that reflected portion back out. So if you've noticed, it gets hot outside, and it's a good thing that we don't absorb 100% of the radiation from the sun, because then it would be a lot hotter. So you have some percentage of the radiation that's coming from the sun that's going to bounce off water, bounce off clouds, bounce off the ground, and go back into space. Generally speaking, the Earth, it's about 30%. Generally speaking, it changes based off of where you are in your orbit, and it can change for what planet you're orbiting. So the moon and the Earth have different albedos, but basically the Earth is about 30%. So 30% roughly of the radiation that's coming in from the sun is going to bounce off the Earth and back onto you. So that's reflected solar radiation. Okay, so that's a lot of heat coming at you. And then you have more. You have essentially conduction from internal heat. So that's your electrical components, your batteries as they charge and discharge. All of those internal components are also generating heat, and you have to care about it. So that's 4 sources. So this is kind of the odds you're playing with. You have 4 against 1. You have 4 sources and 1 way to get rid of it, and that's radiation. And the only way you can get rid of heat is by radiating it away to deep space. So that normally, for small sats, you don't have specific radiators. Like you don't have giant radiators that's trying to radiate away that heat, which is why they're called radiators, because they're radiating away heat. Your car has a radiator. It's not a radiator. It's not radiating away heat. That's not a radiator. That's a condenser. It's not a radiator, but they call it a radiator for some strange reason. So that's if you're in the sunlight. Then imagine you're all the way over here, and then you're in eclipse. Well, then it's basically 2 against 1. So you have Earth IR, because the Earth is always radiating away heat no matter what direction you are, but you don't have direct sun because you're in eclipse, and then you also don't have reflected solar because you're in eclipse. Then you also have to deal with internal heat as well. So obviously, if you look at this, I have 4 sources and then 2 sources. I'm going to be colder in eclipse and then hotter in the sun. If that sounds kind of, well, oh, that's really simple. Why is it so hard? Then, well, you're right. That's really simple. It's not actually that hard. This looks bad. It's not. Basically, the entire thermal design of a satellite comes down to one simple equation, which is I have heat in minus my heat out equals my heat stored. Stored can trip people up. What do you mean I'm storing heat? I can't store temperature. No. What that really means, Q stored is Q net. So classic differential equations example in class is you're pouring water into a container, and the container has a hole in the bottom. You know, I have rate out and rate in. Please tell me what's my rate of change in that container of whatever. Super simple example. That's actually what that is. It's just a measure of, am I gaining more heat than I'm losing, or am I losing more heat than I'm gaining? the standard terminology or semi-standard is storage. So am I storing away heat because I'm gaining more than I'm losing, or am I removing stored? Words don't really work for this one as well, but basically it's the idea, am I gaining more than I'm losing? Q solar, those are all Q dots. They exist in the crack on the wall there, but they're Q dots. You have QN, so you have Q solar, Q albedo, the IR flux, and the internal heat generation. All of those are in units of watts. So that's regular energy. Technically, it's watts or joules per second. It's actually energy rate, not total energy. You're not trying to sum up the total energy of your satellite. You're trying to sum up the energy rates. So you have all of the equations that describe your rates in, and then you have one rate out, and then you have your basically rate of storage. I'm going to go briefly over these equations. Look at this later and dive into it more, because I'm not going to try and explain all of this in one talk, because that would be more of like an actual college lecture, which I'm not doing. But some of the key things you want to look at there, though, is notice how area, the big A, is always there. So the more area you have, the more collection area you have for all of those radiation terms, and also the more area you have away for getting rid of your heat. So it's a 1-to-1, more area, more heat input, and also more heat output at the same time, but they scale differently. For heat out, it is proportional to temperature to the 4th power. So there is some nonlinearity there that can make your simulations interesting. If you have questions about that, ask me after this talk. And then you have Q stored. So basically that is the thermal mass of your satellite. So thermal mass, how do you get that? Average density of your satellite, more or less. You have your specific heat and then your volume, and then you get thermal mass from that. So you're basically saying, do I have a lot of thermal mass or do I have a little bit of thermal mass? Think about it like this. If you have a giant piece of metal, that's going to hold a lot of heat for a long time. Anyone who's cooked knows this. If you have a pan on the stove, you cook something, you come back 30 minutes later, and it's like, gosh dang, that's still really hot. Why? Well, it has a lot of thermal mass. If something is very, 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 very thin, like aluminum foil, I don't know why I always pick kitchen and cooking examples for this, but if you have aluminum foil and you stick it in the oven and then you pull it back out, you can touch it in like 2 minutes because it doesn't have a lot of thermal mass. It's very, very, very thin and has a lot of radiation area. So it can really, really easily get rid of all of that heat because it has a lot of ways to get rid of that heat. But a giant block of aluminum or a pan you stick in the oven is still going to have a lot of heat because it has so much more thermal mass. That's the difference. If you want to get a good like hands-on feel for thermal, just go cook something for a while, and then you'll start to see kind of what we're talking about here. Satellite properties or material properties. You need traceability, and you also need to make sure you have all the correct information. So as you're going through and you're talking with people about their different subsystems, you're going to want to start basically making tables and saying, okay, what materials do I have? In this case, an example, like I have aluminum 6061. I have a PCB that's 4.6% copper. I have some solar cells. What are their thermal conductivities? What's their densities? What's their specific heats? What's their absorptivity? And then what's their emissivity? Notice I skipped over absorptivity and emissivity because I'm going to come back to that and talk about that specifically, because that is a tripping point for people. But basically, you want to have traceability for all of the different materials that you have on your satellite. And then you want to make sure that they're referenced. So if someone comes to ask you and says, hey, you know, where did you get that number? That doesn't make sense. You can say, oh, well, I got it from that reference. This is kind of like doing your homework right. Like you want to make sure that you show your work. So this is showing your work. You're going to want to talk about 2 specific types of properties, though. One is thermophysical. So that's your density, your specific heat. That's actually like the physical properties of that material as it relates to conduction. Then you have thermal optical properties, which are absorptivity and emissivity. Absorptivity is how much, a fractional amount, how much of the sun's radiation do I absorb? If I have an absorptivity of 1, I absorb all of the incident radiation that I collect. So like if you have a giant solar panel, if it has an absorptivity of 1, I'm going to absorb 100% of the solar flux coming into that solar panel. That's kind of a bad thing because that means you're absorbing a lot of heat. An absorptivity of 0 means that I absorb 0% of the incident solar radiation. Everyone tracking with that? Okay, that one's simple. Emissivity is a bit different. Emissivity is both a description of absorption and emission. So what do I mean by that? In this case, emissivity is a description of infrared absorption. So if you're talking about how much of the radiation flux coming from the Earth am I absorbing, you don't do absorptivity. You don't use it. That's for sun. You use emissivity. So if I have an emissivity of 0.5, I am absorbing basically 50% of the incident flux coming from the Earth, because it's a description of infrared emission and absorption. If I am facing deep space and I'm wanting to think about radiation, how much radiation am I actually emitting? I also use emissivity because it's also a description of emission. So I could have an emissivity of 0.5, which means I'm essentially, this is not technically the case. Don't go to your heat transfer professor and quote this to him, but essentially it means I am emitting at around 50% capacity. That's just a simple way to think about it for the non-thermal engineers in the room. Basically, emissivity of 1, I'm radiating a lot of heat. Emissivity of 0, I'm emitting 0 heat. Emissivity of 0.5, somewhere in the middle. So you do need to track absorptivity and emissivity. It is hard to get those properties right because no one who makes materials really bothers to get good, accurate emissivity measurements. So a lot of times you're kind of stuck with being like, well, I don't know. It's a plastic. I don't know what it is. But, well, a similar plastic has this optical property. And so absorptivity and emissivity, I'll just use that one. And a lot of times that's what you're left with. Different aluminum finishes will have different emissivities and absorptivities. So if you have a brushed aluminum versus a polished aluminum, those are going to have different optical properties. Reference the Thermal Bible, i.e. Thermal Control Handbook. It lists a ton of thermal, physical, and thermal optical properties. Start with those, and if you can get better measurements, then do so. Basically, satellite material properties, you have to keep track of all of your properties for your sim. Okay, the thermal modeling process. For those of you who actually have to deal with this, now you're like, oh, finally, we're getting to the thermal modeling portion of this thermal modeling talk. Yeah, that's the way it is. You spend 90% of your time worrying about everything else and 10% of your time actually doing the thermal model. So the process, I'm gonna stick on this word. It is a process. It is not a one and done. Thermal modeling process is the process of modeling a satellite's thermal characteristics. So all of the thermal properties, so all of those guys, it's the process of modeling these guys using representative thermal geometry. I cannot beat this one over the head enough. Thermal geometry. Okay, if you take one thing from my talk, one thing, please take this one. Thermal geometry and CAD geometry are not the same thing. I'll say it again for those in the back. It's not the same thing. Do not take your CAD geometry of your spacecraft, import it into your thermal modeling software of choice, mesh the darn thing, and use all of the geometry. That is a recipe for disaster. Don't do it. They are not the same thing. CAD geometry is a description of reality and a description of the physical parameters. That is not the case for thermal geometry. What is thermal geometry, then, you say? It is the description of the thermal geometry, the thermal parameters, i.e., if you have this wooden table here and you input heat onto one edge, say there's a giant heater that's on this edge, is heat going to be flowing up and down through that thin surface? No, you're inputting it on the side. How is heat going to flow? It's going to flow through it in 2D. So left and right, and then forward and backward for the table, essentially. What's the thermal geometry then? Is it a cube? Not really. Is it a rectangular surface? Yeah, kind of. Yeah. A lot of the thermal modeling process is transforming your CAD geometry, simplifying it so that way it can more accurately describe the thermal characteristics. So if you have heat that you know is going to be flowing mostly in 3 dimensions, then model it as a 3D solid, like a cube or a 3D cylinder. If you know that's only really going to be going in 2 directions, like a planar heat flow, just model it as a surface. Like, you don't need to know all of the temperature gradients through it. Just model it as a simple surface. It's so much better. If it's only flowing in one direction, then you may not even need to model it as an entire solid or surface at all. You might just need to say, oh, well, I have heat flowing from this point to that point, and you just assign a number to it, and you're done. The thermal modeling guide gets a lot more in depth onto what this means. It's very difficult to describe in 5 minutes. So just kind of take that as just a general thing. Generally speaking, you actually deal with thermal geometry whenever you're doing hand calculations, because if you're doing it by hand, you can't model the entire heat flow through a super complicated structure. You're approximating it as your professor told you to. Well, just approximate it as this shape and that shape. That's that process. You represent it as something simpler so you can actually do the math. So other things, we kind of already gone through this, but another part of the thermal modeling process, you're characterizing the mission modes. What's my cold case? What's my hot case? What's my orbit? What are my material properties? What are my heat loads? What are the geometry and heat flow paths? You're characterizing all that information and then putting it into a model. This is another duh. Why am I sitting here and you're telling me this information? But it's really important. Everything has a temperature. Some people actually kind of forget this whenever they're doing engineering, but everything has a temperature. This microphone has a temperature. You have a temperature. It's normally around 98.7 degrees Fahrenheit, unless you're sick. Everything has a temperature. The importance there is that if everything has a temperature, you have to understand how heat and temperature is going to flow. Heat is a bit of an interesting term. What you're really describing there, whenever you're saying there's a lot of heat flow, is that there's a lot of energy flow that we sense through temperature, or we describe using temperature. And then the more touchy-feely word that we use is heat. It is either very, very hot, i.e. has a lot of heat, or it's not very hot, doesn't have a lot of heat. Yeah, I mean, that's kind of the way you describe it. But basically what you're getting at, though, is that something either has a higher temperature or a lower temperature. Temperature flows like water. High temperature always flows to low temperature. Heat transfer flows downwards. Unless you expend energy, you can't make a colder thing colder and then make a hotter thing hotter unless you expend energy. So why is this important? You need to condense the information about an object and start representing it in a simpler manner and say, okay, I might not be able to model an entire satellite or an entire component, but I individually, I can't go through and model everything about it, but I can condense the information into something simpler. And this is called a thermal node. What is a thermal node? A thermal node is the fundamental building block of a thermal model, and it describes everything that it represents. I'm going to say that again. It describes everything that it represents. That probably sounds super abstract, but work with me on this one. If you say that you have a single thermal node that represents an entire solar panel, that thermal node is describing thermally all of the solar panel's thermal properties. What that means is, if you were to model an entire solar panel as a single thermal node, you condense all of the thermal information about that solar panel into a thermal node. So it's thermal mass of the whole solar panel, its optical properties, it's all of that information. You condense it down and say, okay, well, I have a single thermal node, and then that single node has a temperature that then describes everything that it represents. See how that works? So if I have a lot of thermal nodes to describe a solar panel, I'm no longer describing all of the solar panel with a single node. I'm describing it with many nodes. Same thing with the rest of the satellite. You can represent a satellite with a single node. This is why we give you these single node or one node thermal problems. You're describing all of the satellite with that thermal node then, with the thermal properties. You basically then start increasing your thermal nodes. More thermal nodes roughly means more thermal fidelity. So you're going to go through and you're going to start having geometry. That geometry contains the thermal nodes. And then you're going to start connecting them in thermal networks so that we can see how the heat will flow through all of these different nodes. This is all very, very into the weeds. But the point here is that you start condensing the information and say, I'm not going to represent everything, but I'm going to represent some of it. Okay, so you have three things here that whenever you're dealing with representing a satellite in a thermal model, you have geometric fidelity, resolution, and accuracy. And those three things are different. So fidelity, that is how much correspondent with reality. Remember whenever I said, don't bring in a CAD geometry into a thermal software and then try and mesh the whole darn thing? That is essentially a 100% fidelity because you're 100% representing reality in your thermal software. So less fidelity means that you simplify it. Accuracy is a measure of how well your model's results are correspondent with reality. So if my satellite gets to around 50 degrees C in orbit, and I model it to also say, well, it's probably going to be around 50, you have really, really good accuracy. If your model says it's going to be 20 degrees Celsius and it ends up being 50, that's not very accurate. And then resolution. So this is to what degree of precision the results are known. So this means that, well, I think the whole thing's about 20. That's not a very, very precise statement. It's just kind of like generalized statement. There's not a lot of resolution there. And that's correspondent to having a thermal model that doesn't have a lot of resolution either. It's very, very coarse. However, you could say, well, that component's 20, that component's 22, and that component's 25, and the solar panels are 40. That is a higher resolution because you're describing more information. These three things play together in some interesting ways, such as this. So demonstration of accuracy, fidelity, and resolution. So what am I actually describing whenever I say resolution? So normally resolution is correspondent to your number of nodes. Take a representative bracket. This is actually an isospace bracket pulled from a 3U CubeSat model. This is a simple bracket. It's made of aluminum 6061. And let's say for whatever reason, you want to know how heat flows through it. Okay, well, you make a thermal model and you do something bad, which is you import the whole CAD model into Thermal Desktop and then you mesh it. So like kind of like SolidWorks and ANSYS where you have to mesh something. And then you mesh it. It comes out with 415 nodes in something that's literally 3 inches long. And it gives you a certain heat map. And you're like, hey, cool. I know what the temperature of the thing is. That's actually kind of cool. Yay, I did my job right. Well, sort of. Let's then say that I represent it with just simple surfaces. So then you're looking at the 15 node one. That is a pseudo 3D model because I've made surfaces in one plane and then I've made surfaces in another plane to approximate what that bracket actually looks like in reality because how heat's going to actually flow through it. And then you look at the heat map and you're like, oh, wow, that looks almost identical to the other one, the 415 nodes one. That's cool. Question, do you need then 415 nodes to describe that bracket? No, you don't. Okay, well, make it simpler. If you can kind of see, the 15 node one has extra resolution to it, that fidelity where I'm describing how heat's going to kind of open up at the end of those brackets and then condense down whenever it's traveling through the middle. Well, I've modeled that, but let's say I don't care about that. Let's just say I care about, well, there's going to be heat flowing in this plane and this plane because I have this kind of like a L-shaped surface. Well, I condense it down and I have the nodes again down to 6. That heat map still looks identical, doesn't it? Do I need to add that extra fidelity then? No. Okay, well then look at just that 2-node model. Just a single simple surface with 2 nodes, one at one end and one at the other. Does the heat map look identical? Yes. So which one can I use? Theoretically, you could use whichever one you wanted to, but why spend the extra complexity and time using the 415 node one that's just going to add runtime through your thermal sim? Just use the 6 node or the 2 node. That will work fine. So what's happening here is that you're going from a high resolution and high fidelity to a low resolution and low geometric fidelity. Note there, geometry fidelity. I'm not representing that CAD model 100%, but I am thermally representing it correctly. So I have still a high thermal fidelity, i.e. my model is correspondent to the temperature and thermal reality of the situation, but not the geometry, the physical geometry. And that works. This is the process that you follow for everything on the satellite. Another reason why you don't want to use too many nodes, because it makes models slow, it can add poor predictions, and they're complicated to debug, so you don't know if you did it right or wrong if you have lots of nodes. A satellite of 3U size for you all, and this is in the thermal guide, should only have somewhere between like 200 and 400 thermal nodes total, if you're doing it right. If you have a complicated situation, maybe more. If it's really simple, maybe even less. But the idea here is that if you come to a thermal presentation in whenever your design review is, and you come up there and say, I have 2,000 thermal nodes and you have a 3U spacecraft, we're going to immediately ask you, why is your thermal model that complicated? Maybe you did it right because you say, I have this really unique situation here and I really, really care about temperature. So I really, really need to know down to like the single Kelvin digits of what my temperature is. Then we'll say, okay, well, good job. On the other hand, if you say, it doesn't really matter, I just did it because I could, we're just like, but why? It just makes it harder. So this is how you do geometric fidelity, resolution, and accuracy. I still have accuracy, but low resolution and low geometric fidelity. Makes it simpler. Quick practical considerations, though. Some components will need more resolution than others, more time and care. Components such as electrical components like transmitters, processors, batteries, those are going to require more time and effort to model correctly than a simple structure. Why? It's complicated. Read the thermal guide and you'll find out. But basically, components that are complicated are also going to be thermally complicated. Is a bracket thermally complicated? Not really. It's aluminum. It's going to conduct heat like metal conducts heat. It's not going to be that complicated. Is a processor with multiple different heat inputs at different places going to be kind of thermally complicated? Yeah. So where are you going to spend your time? On the complicated ones, not the structure. The worst example, and I'll close with this, is that I went to SmallSat last year and there was a presentation where a guy literally has a metal plate. He imported it into Thermal Desktop, meshed the thing. It had like 2,000 nodes for a single just metal plate, and he used that in his thermal model. And I'm going, it is a simple metal plate. Why are you using 2,000 nodes? It only needs like 4. Don't be that guy. Be the person that knows this doesn't need that much work. That needs more work. And I'm going to efficiently use my resources because remember, everything you do impacts everybody else. So if you're sitting there making everything too complicated and complicating the results, that's going to affect everyone else. So it's not just about you. Make sure that what you are doing as a thermal engineer plays well with other subsystems. Make sure they're getting the information that they need and that you're doing your job in a manner that is efficient and supports the team and isn't focused about understanding all of reality. Just understand what you need to know to get the mission done. So it's all mission focused. So questions? Okay, thank you. Okay, that was a lot of information. So there's got to be something. Yeah. Unless you're in like geocentric orbit with a military spy satellite, you're probably not going to care. That's kind of the thing with a lot of satellites is that most of the time you're not going to care. The most a company is ever going to ask for in terms of fidelity is down to 1 degree Celsius, maybe, and that's rare. You're more operating on the order of 5 to 10 degrees Celsius, and at that point, radiation off the moon is not going to do anything. Thank you. Hope it was helpful.